Hello, this is Dr. Hanaa Assil, and this is a review on Unit 6. This is in the International A-Level Pearson Edexcel Chemistry, and we're going to talk about the different experimental techniques. So, first of all, we know that we should take some safety precautions in the laboratory. For example, if we're working with flammable liquids such as ethanol or an organic compound, we should heat it in a hot water bath. Keep it away from open flame. If we're doing experiments involving gases, whether it's an experiment that uses gases or produces gases, then we should do the experiment in a fume cupboard. If we're holding hot objects, we should hold them with tongues. Usually, safety precautions could involve wearing safety glasses to avoid splashes in the eye if we're talking about liquids. If we're working with corrosive substances such as acids or bases, then we should wear gloves. So these are some safety precautions. Now, we should be familiar with the hazard labels. You should know the meaning of each of these hazard labels. Something that is a health hazard or flammable or toxic or oxidizing or corrosive, environmental hazards. All of these labels we should be familiar with. Another technique would be separation of immiscible liquids. For example, if I have an aqueous layer and an organic layer, so something like water and hexane, for example, then we can separate it by using a separating funnel, or we refer to it as separatory funnel. Usually, in some cases, we add sodium chloride to the mixture. So if we're saying we're going to add sodium chloride to the mixture, this is so that it dissolves in the aqueous layer, making it denser, and the separation would be easier. Usually, how do we use the separating funnel to separate immiscible liquids? You should know that, first of all, if I have a mixture and we're trying to separate the immiscible liquids, then close the tap and the stopper, shake the funnel and invert it several times. From time to time, we invert the funnel and open the tap. This is to release any pressure that builds up due to formation of gases while we're shaking. Then we're going to leave the layers to settle down, so allow the layers to settle down, and then we need to open to release the lower layer first, but before we do that, we should remove the stopper. So the stopper is opened to allow air in, to balance the pressure inside the funnel, and then the lower layer can be allowed to flow out into a container. Close the tap, put another container, and allow the upper layer to go into the second container. So this is how we use a separating funnel. What if we're trying to separate an insoluble solid from a mixture? In that case, whether it's an insoluble solid or it is crystals that we're trying to collect, then we do filtration. And we can either do filtration using a normal filter funnel and filter paper, or we could do filtration under reduced pressure. In this case, we use what we call a Buchner funnel. This is a ceramic funnel with holes, so it has a porous base. And we put the filter paper on these holes, and this allows filtration under pressure, because when we connect this to the pump, then the pump sucks the filtrate through the filter paper. Of course, the filter paper should be placed so that it is horizontal, covering the holes at the bottom of the funnel. we shouldn't have a curled side, or the side should not be curled, because if they are, then some solid may pass through from the sides and pass through the holes and be lost. How do we do recrystallization? So if we have impure crystals and we're trying to crystallize them again to obtain pure crystals, this is recrystallization. So what do? Dissolve the crystals in a small amount of solvent, that depends on what we're talking about, and then heat to boiling or heat to point of crystallization, filter while it is hot. Now, if we say why are we filtering while it's hot, this is to remove the insoluble impurities. Then we're going to take the filtrate in this case, allow the filtrate to cool to form crystals, and then filter the crystals again. Now, this second filtration is to remove any soluble impurities from the purified crystals. We wash the crystals with a few drops of whatever solvent we were talking about, dry between filter papers. Usually, if we do any reaction and we try to weigh the crystals obtained, usually the actual mass of the crystals is always less than the theoretical yield. It's less than the mass that we calculated that we should have obtained. Now, why are the final crystals less than the theoretical yield? This could be because I started with something that was impure. So when we say we weighed a certain mass of whatever reactant we started with, that was impure, so that mass was not correct. Or the reaction was not complete, so we did not get all the product we were supposed to get. Or while transferring and recrystallizing, we lost some of the product. To determine the melting point of a solid, we use this kind of apparatus. This kind of apparatus is called a Assil tube. This is something with a side arm, and the side arm is heated. It contains paraffin oil, so when the side arm is heated, then the heat is distributed through this side arm by convection currents. The stream, initially when we heat it, the solid, if you notice, is inside a capillary tube. So when we start heating the solid, initially there is a stream of bubbles in the capillary tube. And if we say where did these stream of bubbles come from, this was air trapped inside, and it expands when the capillary tube is heated. And then there is a continuous stream of bubbles coming from the capillary tube, and once the compound is drawn up into the capillary tube, that means it has all melted. We stop the heating and record the temperature. What if my solid is impure? How do we determine if a solid is pure or impure? This is by measuring the melting point. So if we have a solid and we're trying to determine its purity, we determine the melting point. If it is pure, it would have a sharp melting point, and the melting point would be the same as the data value. But if my solid is impure, then it will have a lower melting point than it should have, and it will melt over a range. It will not melt sharply at a specific melting point. It will melt over a range that indicates that it is not pure. Now, when we use this apparatus and we determine the melting point of the solid, the results obtained on different days may not be the same. So if I test the melting point today and on another day, it could be different. This is because it depends on changes in the atmospheric pressure. To cool a reaction, sometimes we're dealing with a reaction that becomes very exothermic, so it becomes very hot. We don't want it to become very hot, so we need to cool it. And this is done by putting the flask into an ice water bath. So we do that to cool down the reaction mixture. This prevents its temperature from going up very high, because that could lead to further side reactions that are not wanted in our experiment. To dry a liquid, how do we dry a liquid? We know that to dry a solid, we dry it between filter papers. Now to dry a liquid, we add a dehydrating agent. So something like anhydrous calcium chloride. Anhydrous calcium chloride will soak up or will collect any water present in the solution. Now, how do I know if it is dry or not? The liquid that is not dry is usually cloudy. So if I have a liquid with water in it, it is cloudy. But once we add anhydrous calcium chloride and stir, then this cloudy solution becomes clear. Then I know it has become dry. If it does not become clear, then we need to add more drying agent in order to remove the water so that the solution becomes clear. What if I want to purify a liquid? So to purify a solid, I do recrystallization. How do I purify a liquid? This is by simple distillation. Now, if my liquid is something that is flammable, that means I need to heat it in a hot water bath and connect it to a condenser. The liquid boils, goes into the condenser, and it is cooled and condenses so that the liquid collected in the conical flask is a pure liquid. When do we do heating under reflux? We do heating under reflux if we want to heat a reaction mixture for a long time, so that I make sure that the reaction is complete, but my reactants are volatile. So I have to keep the condenser vertical like this in order to prevent the escape of volatile reactants. So if, for example, in our syllabus, we need to heat ethanol or an alcohol with an oxidizing agent. Now, if I heat a primary alcohol with an oxidizing agent, I need to heat it completely in order to reach so that everything changes into an acid. If I don't heat it completely, it becomes only aldehyde. So I want to heat it strongly for a long time so that all the alcohol changes into acid, but that means the alcohol would evaporate. The alcohols are very volatile, so I need to put the condenser in this position so that any reactant that evaporates is cooled and goes back down into the pear-shaped flask. So this is heating under reflux, when we're heating something that's volatile and we need to heat it strongly. When do we use steam distillation? This is when I'm trying to heat a liquid, but I don't want to heat it strongly because the liquid decomposes easily. So if we're trying to heat reactants that decompose easily, I could do that by steam distillation. So I heat the flask on the left that contains water. The steam goes into the flask containing the reactants. This helps to get it to evaporate quickly without being heated strongly. And then the liquid evaporates, cools, condenses, and is collected in the pear-shaped flask on the other end. What if I want to show the presence of optical isomers? What do we do? Of course, you should know that optical isomers rotate the plane of plane polarized light in opposite directions. So to identify or to distinguish optical isomers, I can use a polarimeter. Sometimes we pass the gases through U-tubes like this with solids in the U-tube. Now, these solids could be what? They could be solids that we need to absorb water from, or water vapor from the gases going through. So in that case, the U-tube will contain anhydrous calcium chloride. We said anhydrous calcium chloride is a substance that absorbs water. Now, what could solid N be? Well, if it is something that I want to absorb carbon dioxide, then that substance N would be soda lime, which is actually potassium hydroxide. To determine the mass of water in a hydrated salt. So I have a hydrated salt and I want to know the mass of water in order to calculate the value of X. How do we do that in the lab? Well, we weigh a certain mass of the hydrated salt in an evaporating dish using balance. Then we heat to evaporate the water, allow it to cool, reweigh, and then I repeat that, reheat and reweigh until there is no further change in mass. So how do I know if all the water has been lost? If the mass no longer decreases, and then the difference in mass would be the mass of water. We use indicators in titration, and you know that an indicator is a substance that has different colors in acids and bases. So for example, in litmus, you should know that acids will cause the litmus paper to turn red, bases will cause the litmus paper to turn to blue. So this is how we identify whether a solution is an acid or a base. But if we know exactly, we want to know exactly pH of the solution, then we use a universal indicator paper. This shows the pH of the solution and whether it's a strong acid, strong base, weak base, and so on. But in titration, we need an indicator that's a solution. So we can either use phenolphthalein or we can use methyl orange, and you are required to know the colors. So if we have a base like sodium hydroxide in the flask, we start with phenolphthalein, pink, or we start with methyl orange, would be yellow. And then if we do the titration at neutral, the phenolphthalein would turn colorless, that pink color would disappear. If we were using methyl orange and neutral, the color will become orange. How do we do titration? You should know we put a specific amount of the base, for example, into a flask using a pipette, and then we add acid from a burette until the color of the indicator changes. Now, you should realize, first of all, when we read a burette, the eyes should be on the same level as the meniscus, and we read the bottom of the meniscus. So this one, for example, is 24.2 centimeter cubed. You should know how to calculate percentage error or percentage uncertainty. Now, when we're taking readings in a burette, you should realize that we take initial reading and final reading. Now, if we are told that the percentage error in each reading is 0.05 centimeter cubed, plus or minus 0.05, but we read it twice, so that should be times 2, and we'll be required to get, for example, what is the percentage uncertainty for a certain reading. So if we use the burette, for example, to measure 25 centimeter cubed of solution, then the percentage uncertainty will be the initial uncertainty times 2. So if we're told it's 0.05, that's times 2. Over the reading that we took times 100, and that means the uncertainty is plus or minus something percent. Again, if we're using a thermometer Also, the percentage uncertainty would be twice what we're given, because when we read a temperature change, for example, we're told that the temperature rise was 12.5. Well, that means I read an initial reading and a final reading. Each reading had an uncertainty of plus or minus 0.25. So the percentage uncertainty in my temperature rise is the uncertainty times 2 over the reading times 100. So this is plus or minus something percent. Remember that when we're doing titration, I need to rinse the burette first with water. Why? To remove traces of any previous solution for which the burette was used. And then I need to rinse it with the solution that I'm going to fill it with. Why? To remove the water. Because presence of the water in the burette would change the concentration of the solution I'm filling it with. So remember, we rinse the burette twice, once with water to remove previous solutions, and once with the solution I'm going to fill it with in order to remove the water, and then I fill the burette. You should know that a titration should be repeated more than once. I don't do the titration only once. I need to repeat it several times until we reach concordant results. And you should know, concordant results means results within 0.2 of each other. So results that are, the difference between them is not more than 0.2. So if a student did these experiments and he got these results, which of these are concordant? Well, they are the ones that are within 0.2. So the difference between these is 0.2. And the difference between them and this one is less than 0.2. So all of these are concordant. When we calculate the average, we use only the concordant results. We ignore the result that is away from the rest, and that means we divide these, for example, by 3. How do we prepare standard solutions? Standard solutions are solutions that have an exact concentration, and we usually need to do that in order to use them for titrations. So how do we prepare a standard solution? Well, first we weigh a certain mass of the solid using a balance, and then put into a beaker, add distilled water, stir with a glass rod to dissolve the solid, and then transfer the solution to the volumetric flask using a funnel. We wash the beaker with some distilled water, transfer the washings to the volumetric flask, and then we add water to the volumetric flask slowly until the bottom of the meniscus is at the mark in the neck of the volumetric flask. We close the stopper, shake and invert several times so that we're sure that all the solution is the same concentration. So, how do we do the titration to determine the concentration of a specific solution? So, we want to get concentration of an acid. Well, we put a specific amount of base, 25.0 centimeter cubed of sodium hydroxide, into a flask using a pipette. We add 3 drops of an indicator. If that is phenolphthalein, then my solution would turn pink. Then we wash a burette with distilled water to remove traces of previous solution, and then with the dilute acid that I'm going to fill it with to remove traces of water. And then I fill the burette with dilute HCl using a funnel, read the initial reading by looking at the bottom of the meniscus while keeping the eye on the same level with the meniscus. And then we add dilute HCl from a burette until the pink color disappears. We said phenolphthalein in base, it's pink, but once it is neutral, the pink color disappears. We usually use a white tile below the flask to see the color change clearly. Note the amount of acid used. This is the rough estimation of the endpoint. We repeat the steps by adding acid drop by drop slowly. When near the end point, repeat until the results are concordant. Calculate the mean titer and use it to determine the concentration of the acid. What if we're titrating something that has iodine in it? So a reaction that is starting with iodine or is forming iodine, then in that case my indicator is starch. So when a reaction involves iodine, the indicator uses starch. In presence of iodine, starch gives a dark blue-black color. Now, when the iodine is used up, then the blue color disappears. So I can do reactions that produce iodine, and when they produce iodine, I then titrate with sodium thiosulfate. So the action is forming iodine. The iodine in solution is reddish brown. It is titrated with the sodium thiosulfate until the solution becomes yellow, and then I add the starch. So we don't add the starch at the beginning because the color will be too dark and we will not see anything. But we titrate a little bit until there is only a little bit of iodine in the solution. Then we add the starch. The thiosulfate is then added until the dark blue-black color disappears and we know the final volume. So for example, this is a reaction that forms iodine. This is copper ions reacting with iodide to form iodine. Now, the mixture containing iodine would then be titrated using the sodium thiosulfate of known concentration using starch solution as an indicator. The end point is determined when the dark blue-black color is colorless, and the number of moles of iodine can then be calculated and used to determine the concentration of copper ions in solution. In another experiment, here we have hydrogen peroxide reacting with iodide ions and iodine is formed. Now, how do we follow this reaction? We added sodium thiosulfate at the beginning into a conical flask with starch solution and iodide ions and hydrogen peroxide. And then we measured the time taken for the solution to turn blue-black. Now, what is happening here? We're not titrating, but we added the sodium thiosulfate at the beginning so that the sodium thiosulfate reacts with the iodine as it is formed. So, as the reaction forms iodine, sodium thiosulfate reacts with it. It sort of uses it up from the mixture until all that specific amount of sodium thiosulfate has been used up. Then any iodine formed after that reacts with starch and gives a blue-black color. This is in order to allow the reaction to occur before the color change is observed. I don't want it to turn to blue-black immediately from the beginning of the reaction. I need to allow the reaction to proceed for a certain amount until all the sodium thiosulfate has been used up, and then we see a color change. Another reaction is to determine percent copper in brass. Now, this kind of question is repeated a lot. We have brass. You know that brass is a mixture of copper and zinc, and we're trying to determine the percent copper in a certain mass of brass. So the first thing we do is weigh the sample of brass, place the brass in a beaker, add concentrated nitric acid. Nitric acid will dissolve the copper, transfer the solutions and washings to a 250 centimeter cubed volumetric flask, make the solution up to the mark with distilled water and mix well, and pipette 25 of that into a conical flask. Neutralize the excess nitric acid. Of course, this is by adding sodium hydrogen carbonate or sodium carbonate. Add 10 centimeter cubed of potassium iodide solution to the conical flask. Titrate the iodine produced with sodium thiosulfate using starch indicator and repeat the titration. We can use this to calculate how much copper there is in the mixture. We could also have titration with potassium permanganate, and you should know that potassium permanganate originally is purple. So in this case, we do not need an indicator. We say this is self-indicating. So no indicator is needed if I'm titrating potassium permanganate. Now at the beginning, a reaction occurs and the pink color is removed. So I have in my flask, I have a reagent that will react with the potassium permanganate. So as I add the potassium permanganate, it reacts and the pink color becomes colorless until all the solution in the flask has been reacted. Then the drop of potassium permanganate added after that remains, so my end point is a pale pink color. We could do that also with potassium dichromate, but you should realize that the end point with potassium permanganate is clearer, or it is much better to use potassium permanganate as the oxidizing agent used in the titration, because the color change or the end point is more clear than when we use potassium dichromate. When we want to calculate delta H for a reaction, of course, we said we do this reaction in a polystyrene cup because polystyrene is a good insulator. There is less loss of heat to the surroundings. And to determine the temperature rise when we dissolve the solid, what do? We use a stopwatch, measure the temperature of water every 30 seconds for 3 minutes. So we have a reaction happening and we want to determine the delta H for that reaction. So I'm trying to measure first the temperature rise. Now, at the beginning, I measure the temperature of the water alone for 3 minutes. And then I add the solid in the water and I continue to record the temperature every 30 seconds until there is no more change in temperature. Then I draw a graph. So, when we plot a graph of temperature versus time. And how do we join it? Remember, we join two sets of points with straight lines. The points that we got at the beginning before I added the solid, and the points that we got at the end. They were two straight lines. I extrapolate them and I draw a horizontal line at 3 minutes. 3 minutes, that's when we added the solid. So that horizontal line is at 3 minutes, and the highest temperature recorded minus the initial would be my temperature rise for this reaction. And then, how do we calculate delta H? We said the temperature rise that we got, we used to in Q is equal to mc delta T. Again, remember that m is the mass of the solution, not the solid. So this is the mass of the water we started with, and you should know that that is the same as volume. So if we say we started with 50 centimeter cubed of water, that is 50 grams, and that is my m. If we added two solutions, then the mass would be the total of the masses of the two solutions. C is a specific number, 4.18 or 4.2, and delta T is the temperature change that we measured. We use the Q, which comes out in joules, to determine the delta H. Delta H is Q over the number of moles of the solid that I dissolved in it. And remember that delta H must have a sign. So if this was a temperature rise, then the reaction is what? The reaction is exothermic, and delta H must be a negative value. If there was a decrease in temperature, then this is endothermic, and the delta H is a positive value. Usually, the delta H that we calculate using this experiment is different or lower than the value given in the data booklet. Now, why is that? This could be because some heat was lost from the apparatus, or incomplete reaction. So if we're burning something and using it to heat the water, then maybe incomplete combustion. Or if we're trying to get the delta H of the fuel, then some of the fuel evaporated, so the mass of the fuel is not accurate. Tests for ions. You should be familiar with this. We've done this in several syllabuses before. So carbonate, how do I know if something is a carbonate? I add an acid. If I add an acid to a carbonate, we get effervescence or bubbles of gas. Now, how do we test the gas? The gas should be carbon dioxide, so it should turn lime water milky. And we can use this to test for acid also. So if I add sodium carbonate to something and we get bubbles of gas that turn lime water milky, that means that something was an acid. Chloride, bromide, iodide. We said we add dilute nitric acid and silver nitrate. The chloride gives white precipitate, bromide gives cream precipitate, iodide gives yellow precipitate. But the problem is these colors are very near to each other, and usually in practice in the lab, it's very difficult to determine if the precipitate obtained was white or cream or yellow. So we need to do a further test. You should, in that case, try to dissolve the precipitate in dilute ammonia. If the precipitate dissolves in dilute ammonia, then it was due to chloride. If it did not dissolve in dilute ammonia, it could be bromide or iodide. So how do we distinguish? We try to dissolve it in concentrated ammonia. Now, if it was due to bromide, the precipitate dissolves in concentrated ammonia. But if it is iodide, then the precipitate will not dissolve in dilute or concentrated ammonia. Test for sulfate, we add dilute nitric acid and barium nitrate, or dilute hydrochloric acid and barium chloride. We get a white precipitate if it is a sulfate. Remember, we add the acid first because we need to remove any carbonate that may be present, because any carbonate present would form a white precipitate even if there is no sulfate. Test for nitrates. Well, we could do a test involving sodium hydroxide, aluminium foil, warm gently. We get bubbles of gas that turn damp red litmus paper to blue. So that's a test for nitrate. Or we could just heat the solid strongly. Now, if this is a nitrate of group 2, it would give metal oxide plus nitrogen dioxide gas, which is a reddish brown gas, plus oxygen. If it is nitrate of group 1, it gives only nitrite plus oxygen. So in both cases, we get bubbles of gas that relights a glowing splint. Test for ammonium ions. We said we add sodium hydroxide, warm gently, bubbles of gas are given off that turn damp red litmus paper to blue. Iron 2, with both sodium hydroxide and aqueous ammonia, we get a green precipitate, insoluble in excess, and if it is left standing, the precipitate turns reddish brown because it becomes oxidized by oxygen in the air. Test for iron 3, whether we add sodium hydroxide or aqueous ammonia, we get a reddish brown precipitate, insoluble in excess. Now, what is the test for amines? Remember, amines are derivatives of ammonia. So if I add ammonia or amines to copper ions, then I get a light blue precipitate that dissolves in excess, giving a dark blue solution. Esters, you should know that esters are known for their fruity smell. So if we are told that a product gives a fruity smell, you should know that that is an ester. Ammonia gas turns damp red litmus paper to blue. Carbon dioxide gas turns lime water milky. You should know that that's because lime water is calcium hydroxide. That's a base. If we react it with the acidic carbon dioxide gas, that causes the formation of calcium carbonate, and that's a white precipitate, and that's why the lime water turns milky. Chlorine gas bleaches litmus paper. Hydrogen and oxygen, you should know, hydrogen gas, we insert a lighted splint, it pops. Oxygen gas, insert a glowing splint, it relights. Flame tests. Remember that flame tests are done on metal ions because metal ions, when they are heated in the Bunsen burner flame, the electrons gain energy and jump to a higher energy level. Now, when they return back to their ground state, they emit the energy that was obtained in the visible spectrum, so they give characteristic colors. So, how do we perform a flame test? Well, we clean a platinum wire by dipping it in concentrated HCl, dip the wire in the salt, expose the wire to the non-luminous flame of the Bunsen burner, that's the hottest part of the flame, and observe the emitted light. Of course, when we're using a Bunsen burner, you should realize that the air holes should be fully open. Remember, if they're not fully open, then the flame is not hot enough. So I want the air holes to be fully open so that we have a blue flame or non-luminous part of the flame. And of course, you're required to know the colors obtained for the different ions. So lithium is red, sodium yellow, potassium lilac, calcium brick red, strontium red. So remember, strontium and lithium were red, and barium is green. What is the test for water? Well, we use the anhydrous copper sulfate or anhydrous cobalt chloride. And remember that anhydrous copper sulfate is white. When we add water, it turns to blue. Cobalt chloride anhydrous is blue. When it is something that has water or it's a solution, cobalt chloride is pink. Of course, testing for pure water, we said the pure water should boil at 100 degrees Celsius. Alkenes. To test for alkenes, we can add bromine water. So the bromine water turns from orange to colorless, or we could add potassium permanganate. Remember that potassium permanganate reacts with the alkenes, so it turns from purple to colorless. Test for alcohols. Presence of OH in an alcohol or in an acid. You can add phosphorus pentachloride, PCl5. This gives steamy white fumes of hydrogen chloride. Or if we're talking about primary or secondary alcohol, then it can be oxidized by acidified potassium dichromate, which changes from orange to green. Please be familiar with all of this. How do we test for aldehydes and ketones? You should know. Aldehydes and ketones react with 2,4-dinitrophenylhydrazine, which is that benzene ring with 2 nitros and the NH2, that's the hydrazine part. This is a test for both aldehydes and ketones. If we have any of them, we will get an orange-yellow precipitate. And this precipitate can actually be filtered, determine its melting point, and its melting point can be used to identify which aldehyde or ketone we have. But to distinguish between aldehydes and ketones, we can use Tollens reagent that forms a silver mirror with aldehydes only, not ketones, Or we could use Benedict or Fehling. If we add Benedict or Fehling and heat, we get a brick red precipitate with aldehydes. That is because Benedict or Fehling is originally copper 2 sulfate. So when it is heated with aldehydes, it is reduced to copper 1 oxide, which is a brick red precipitate. Test to show the presence of this methyl ketone, which is the CH3 double bond O. So if we have a methyl ketone on one end, we can add aqueous iodine in sodium hydroxide. This gives a yellow precipitate due to the formation of CHI3 and the sodium salt of the rest of the aldehyde, and that gives an antiseptic smell. So remember the iodoform test, iodine in alkaline aqueous sodium hydroxide. This will give yellow precipitate, which is due to the CHI3, and antiseptic smell. Color of complexes. We talked about transition metals and we said they form colored compounds, and that is because the d orbitals that are originally the same energy, 5d orbitals of the same energy. Now when the metal ion forms a complex, the orbitals are repelled by the bonding electrons with the ligands, so the d orbitals split, so the two of them are at a slightly higher energy than the other three. Now when we're talking about transition metals, that means incomplete d orbitals, then electrons can, in the lower d orbitals, can gain energy, jump to the higher energy levels, and the rest of the spectrum or the visible spectrum is transmitted, and this shows a specific color that is observed. So for example, copper 2 ions, you should know that copper 2 ions with sodium hydroxide and with ammonia, they form a blue precipitate. But with sodium hydroxide, the precipitate is insoluble in excess. With aqueous ammonia, the blue precipitate that is formed with aqueous ammonia dissolves when excess ammonia is added. And this is because, remember that copper in water forms a complex with 6 water ligands. So this is a blue solution of the copper water 6 complex. Now when we add ammonia solution, it first forms a pale blue precipitate. But then when we add excess, we have what is called ligand exchange. So the ammonia replaces the hydroxide or the water. So we end up with ammonia and water added to it, so as a complex, and this is a dark blue solution. If we add HCl to the water, the copper water complex, which we said is blue, now if we add HCl to it, it forms the copper Cl4 complex, which is yellow. But between the blue and the yellow, when we have drops of HCl added, then some of the blue has turned to yellow, so actually they form a green solution. And then with excess HCl, this forms the yellow copper chloride complex. So this is a tetrahedral structure with 4 chloride ions and an overall charge of 2- because the central ion has 2+. Each of the chlorides has 1 negative, so we have an overall of 2 negatives. Nickel, please remember the colors. Nickel in water forms a green solution. Now when we start to add ammonia, we have what is called deprotonation. So some of the water, the H is removed from it, so it forms OH instead of H2O, and this is a gray-green precipitate in which the nickel has 4 water and 2 OHs. Now when we add excess, then the excess forms a blue solution in which the nickel is complexed with 6 ammonia ligands. If we add HCl to the nickel water solution, we get a yellow solution of the nickel with 4 chlorides as a complex. Cobalt, you should remember cobalt ions, cobalt 2+, in water is a pink solution. So the complex between cobalt and 6 water is pink. Now when we add hydroxide, remember that we said when we add drops of hydroxide at the beginning, what happens is called deprotonation, removal of hydrogens from 2 of the water, so it forms OH as a ligand, and this is a blue precipitate. So remember that adding sodium hydroxide to cobalt 2 solution changes it from pink to a blue precipitate. Now when we add excess ammonia, then the cobalt with the 6 ammonia is a yellow-brown solution. If we add concentrated HCl to the cobalt water complex, which was originally pink, it now turns to blue, in which the cobalt is complexed to 4 chloride ions. Again, these are tetrahedral with an overall charge of 2-. Zinc ions, whether you remember the test for zinc was whether we add aqueous sodium hydroxide or aqueous ammonia, we get a white precipitate soluble in excess, giving a colorless solution. This is because with sodium hydroxide, the zinc 2+ ions will initially form a white precipitate of zinc hydroxide, but when we add excess, then we have the precipitate dissolving to form this kind of complex. With aqueous ammonia, it's the same. When we add drops, it forms a white precipitate in which we have 2 of the water has been deprotonated to form OH. But when we add excess ammonia, in which the zinc, we have ligand exchange in this case, in which the ammonia has exchanged with the water ligands, then this forms a colorless solution. Vanadium, remember the colors of vanadium. +2 purple, +3 green, +4 blue, +5 yellow. So as we oxidize the vanadium from +2, +3, +4, +5, these are the colors. But what if we start with +5 and we try to reduce it? So for example, I could start with the +5, which is yellow, add zinc. In this case, it will be reduced from +4 to +5 to +4 to +3 to +2. But remember that we said if we have a yellow solution and it starts to turn to blue, in between the yellow and the blue form green. And then it becomes totally blue, and then the green of the 3+, and then the purple of the 2+. Again, if I have 2+, which is purple, and I leave it standing in air, then it will be oxidized by air. But the problem is oxygen is not a very strong oxidizing agent, and what happens is the purple +2 vanadium ions will be oxidized to +3, which is green, but no further oxidation occurs. This is because the oxygen cannot oxidize the +3, it is harder to oxidize, and oxygen is not such a strong enough oxidizing agent. This kind of questions, please note, we have a vanadate 5 solution, and we react it with potassium permanganate, which is an oxidizing agent. Now, what happens is the vanadate first is in the +5. I'm going to reduce it by tin. So when we add tin to the +5, it is reduced. But we're not sure it is reduced to what. Is it reduced to only +4 or +3 or +2? So we add potassium permanganate to oxidize it back to its original oxidation state, which was +5. and we determine how much potassium permanganate was needed, and from that I can determine whether it had been reduced by 10 to +4 or +3 or +2 and so on. So from the amount of manganate, deduce the vanadium ion oxidation state after reduction by 10. So what is happening is I calculate the number of moles of the vanadium 4 from concentration times volume. I calculate the number of moles of manganate needed to oxidize it back to its original oxidation state. And I find that it is 2 moles of manganate reacting with 5 moles of the vanadium. And that means that if from the equation up there, I need 1 mole to react with 5 electrons. Remember, 1 mole of manganate will oxidize it 1 step further. So if I needed 2 moles, that means that the vanadium 5 was reduced to +3, so that when I reacted it with the permanganate, I oxidized it from +3 to +4, and then from +4 to +5. So these are 2 steps that needed 2 moles. Keep that in mind. Chromium ions. How do we identify chromium ions? We know that aqueous sodium hydroxide gives a green precipitate that dissolves in excess. Aqueous ammonia gives a gray-green precipitate that is not soluble in excess. Again, chromium ions, when we start, they are in water, they are green. So the chromium ions in water form a green solution. When we add sodium hydroxide, it causes deprotonation. Excess sodium hydroxide causes further deprotonation, and we end up with a green solution. Now with ammonia, what happens is adding a small amount of ammonia. Again, the ammonia is acting as a base, so we have deprotonation. And then if we add excess ammonia, we have ligand exchange. So we exchange the ammonia for the water complex ligands, and we end up with a purple solution. Oxidation of chromium. We said chromium in water, chromium +3 originally is a green solution. Now if we add hydrogen peroxide is an oxidizing agent. It will oxidize the chromium +3 to the chromate ions, in which chromium is +6, and this is a yellow solution. So remember, hydrogen peroxide on chromium water complex, and chromium in the water, which is green solution. We oxidize the chromium 3+ to chromate, chromium +6. If we add acid to the chromate, it becomes dichromate, Cr2O7 2-, and that's orange. And the orange, again, if we add a base, it returns back to the chromate ions, which are yellow. So how do we test for dichromate ions? You should know that if I have dichromate and I add silver nitrate to it, so we're adding dilute nitric acid and silver nitrate, this gives a red precipitate of the silver dichromate product, which appears as a red precipitate. You should be familiar with this. These ions give green solutions in water. So vanadium +3, iron +2, nickel +2, chromium +3. All of these in water with water ligands forming a complex, all form green solutions. Titanium. We have titanium +3. Titanium +3 in water forms a purple solution, in which we have deprotonation of some of the water ligands. Manganese ions, manganese in sodium hydroxide solution will give an off-white precipitate insoluble in excess. So when we have this precipitate, this is a precipitate in which we have a complex between the manganese and 4 water and 2 OHs. So again, this is a deprotonation of the 6 OH of the water ligands in the manganese. But on standing, this precipitate darkens. It darkens because the manganese 2+ becomes oxidized by oxygen in the air, and it forms manganese dioxide, which is darker in color or forms black precipitate. Reaction kinetics, remember, you should know these. If we draw graphs of rate versus concentration, then if the graph has a horizontal line, it's not affected, the rate is not affected by concentration, this is 0 order. If it is directly proportional, then it's first order, and if it has that kind of graph, it is a second order. And remember that when we determine the order with respect to a certain reactant, concentrations of the other reactants are kept very high. And this is so that they are almost constant, and the rate will depend only on the concentration of the reactant we are changing. To determine the rate of a reaction at a certain time, if I have the graph of concentration versus time, how do I determine the rate at a certain time? For example, I want the rate at 2 hours, then I draw a tangent at the graph at that time, and I obtain the slope of that tangent. That would be the rate at that specific time. The order of the reaction can also be obtained from the half-lives. So if we have concentration versus time, and we're measuring the time taken for the concentration to become half of what it was, if the half-lives are constant, it's first order. If the half-lives decrease, then it is 0 order. If the half-lives increase, then it is second order. Okay, spectroscopy. Remember, if we're looking at the infrared spectrum of an alcohol, what we're looking for is a broad peak at around 3000 and something. If we're looking at the IR of a carboxylic acid, then we have a peak at around 3000 and something, but we also have a peak at around 1700 due to the C double bond O. So if we have both, then we have a carboxylic acid. A ketone would have only a peak at around 1700, no peak in the 3000 region. An aldehyde would have the peak for the C double bond O, but we also have smaller peaks for the CH of the aldehyde before 3000. So please keep all of these in mind. An amide has a C double bond O at around 1700, but also a broad peak for the NH at around 3000 and something. An ester will have the C double bond O for, at 17 something and a small peak before 3000. If we're looking at the proton NMR, remember that the proton NMR, the height of the peak is an indication of how many protons give this peak, and the splitting is an indication of how many protons on the neighboring coordinates. So if we're looking at ethanol, first of all, remember the peak for the OH does not split, so we have a singlet at around 4 point something for the OH. Then we have a peak due to the 2 hydrogens, but so this peak is an intermediate height, and it is a quartet because on the neighboring carbon we have 3 hydrogens. Now the peak on the right is highest because it is due to 3 hydrogens, and it is a triplet because I have 2 hydrogens on the neighboring carbon. We can use also the proton NMR to distinguish between compounds. So if I have a proton NMR, I can tell whether it is due to structure 1 or structure 2. from the number of peaks. So structure 1 has 4 peaks, while structure 2 would have only 3, because all the CH3s in structure 2 are equivalent. In structure 1, it is symmetrical, so the part on the right is the same as the part on the left. Now, the height of the peaks will also be an indication, because in structure 1, the highest peak is for 6 protons, which is CH3 on one end and CH3 on the other. But in structure 2, I have a peak for 9 protons, which are the 3 CH3s that are equivalent. Mass spectrometry, of course, the most important thing is looking for the molecular ion peak, which is the one with the highest M over Z, and that gives me the molecular mass of the compound. We can also use the other peaks to determine the fragments that may be obtained from the compound. Okay, so we're going to end this here. I hope this wasn't too long for you. Please revise all of this and make sure you're familiar with it. Thank you for listening.